Okay, so the next talk will be given by Ankur, also from the Media Lab, coming from the same group. And Ankur will talk about peer pressure in social network.
This is the pointer. Thank you. Hi, everybody. This is a work in collaboration with Iyad Rahman from Mazda Institute of Science and Technology and my advisor, Sandy Pentland. And I'm trying to create a mechanism to induce peer pressure in social networks. So it's very different from the work on peer pressure that you would have seen. So I'd also like to thank Yahoo Key Scientific Challenges Program and Martin Family Fellowship for Sustainability for supporting my work. So for people who do not know about externalities, let me just quickly give an idea that will also explain the title of the paper, or title of the work. So consider we have a networked society, and there are two individuals, A and B, who are consuming a lot of energy that creates pollution and in turn provides discomfort to the whole society. Then that is the externality that these individuals are creating for the whole society. So normally these are selfish agents, so they will try to consume so that their utility is maximized, and in this sense, the consumption of electricity is much higher than the socially optimal level of consumption, right? So this problem has been addressed before, and there's a famous Coase theorem that says that the problem of externality arises because of the absence of clearly defined property rights. So no one knows who owns the environment, so everyone is okay to pollute them. But Coase theorem also says that in the presence of clearly defined property rights and also in the absence of any transaction costs, the people in the society can talk to each other, negotiate, have transfers of payments, and then socially optimal consumption level can be achieved. Right. So the problem is that the last assumption that of absence of transaction cost does not happen. In a network society, no one knows whom to talk to and how to get to that person and how to make the transactions. Right. So I created an idea of localizing these externalities. So the idea is to amplify the externality that is felt by the whole society around the neighbors or peers of the individuals who are creating the externality. And in this sense, the transaction cost can be minimized because people know who are creating the externality, and that way they can actually make transactions and can bring the consumption down to socially optimal level. So I created a reward scenario for this thing. So suppose A consumes a lot of energy. This produces externality on the whole society. But I give reward to the neighbors of the individuals if A consumes low amount of energy, right? So this way, these four neighbors of the individual A can exert peer pressure on, they have an incentive to exert peer pressure on the individual A. And this is the kind of transaction we are talking about. Instead of monetary transactions, the transaction is a peer pressure. And thus, A reduces his consumption. So we want to find a suitable reward mechanism such that in an equilibrium, the consumption profile will be same as the optimal consumption profile, right? So just before we go into the model, I just want to say that there is some experimental evidence that this mechanism works. So we had a collaborator, student who just graduated. She did some experiments in one of the MIT dorms, and she found out that the peer pressure can be introduced by this rewards mechanism, and also found out that with this rewards mechanism, the amount of consumption of electricity and energy can be reduced to a much more as compared to standard solutions such as taxation or subsidies. Right. So let's quickly jump to the model. So we have a social network of nodes and edges, and we have actors I in the network. The actions that actors take is the amount of energy they consume, xi. That will be the action. Right? We will denote the neighbors of each actor as the neighbors of I. And now the utility of the actors consists of two terms. First is the raw utility of consumption, the higher, which is concave in this case, and then the externality felt by the consumption of everyone else. Right? The higher consumption, the total amount of consumption in society, the more externality they feel, right? Which is a convex function and increasing. The strictness is not necessary in this case. So the known result in this is a standard model. The known result in this case is that the equilibrium consumption, which is the x star, will be higher than the optimal consumption, which is x naught, right? And the standard solutions are either by quotas, like give everyone a quota that they can not exceed, or you can actually tax or subsidize the consumption. The lower the consumption, the lower the tax, or the higher the subsidy, right? So let's move on to the model with peer pressure. So this is a new model of peer pressure, presence of externalities when peer pressure is present. This model is very similar to the recent work by Antoni Calvo Armengol and Matthew Jackson. The paper is called Peer Pressure. So from now on, anyone who writes a paper on peer pressure have to refer to that paper. So this utility terms here consists of two additional terms. First, let me introduce what is PJI. PJI is the pressure that actor J exerts on actor I to reduce his consumption, right? So, so this third term here is the cost that a consumer I feels when he experiences total pressure of this and he's consuming xi units of energy, right? And the last term is the cost of exerting pressure. When I exert pressure on my friends, I feel a social cost. So the last term is the social cost. So a very simple way to understand this game is in the form of extensive form game. So in the first stage, actors decide the amount of pressure to exert on each of their peers. And then in the second stage, each actor observes the pressure exerted on that actor, and then chooses the amount of consumption that the actor wants to do. Right? When the cost of exerting peer pressure is substantial, which is in most sense higher than the marginal cost of marginal externality felt by the users, the peer pressure is normally lower than the optimal peer pressure in the equilibrium, and the consumption is higher than the optimal. Right? So now what we did is that we introduced a reward mechanism. So we made a little change. We add an additional term, which is a reward. So people get rewarded for their neighbor's low consumption. So we created a reward function, which is, I'm sorry, this is cut. OK. So the reward, we have a reward function here. So an actor I receives a reward rj I of xj for his neighbor j's consumption when the consumption is xj. Right? So I receive reward for each of my neighbors, each of my peers, low consumption. Right? So now we have this idea. Now the important question is, what should be the right reward function? Right? So we characterize the reward function. We first identify what are the desirable properties of the reward function here. So the first condition is that we should have a subgame perfect equilibrium in the two-stage game that I introduced in the previous slide. And then the second condition is that the equilibrium consumption should be optimal. Right? So these two conditions actually provide constraints on the marginal reward or the derivative of the reward. Right? So but they do not fully characterize the reward function. Right? Then we have two additional constraints, conditions. First thing is that the reward should be simple enough to explain to people so that it can be actually implemented. So let's restrict the rewards to the set of linear functions. Right? Okay, the reward functions could be a set of linear functions. Now then, which are simple to explain to people. Then our goal is to minimize the budget for the rewards. So what should be we want to spend the minimum amount of money to give the reward and still achieve the socially optimal outcome. Right? So these four conditions actually fully help us identify the reward function. And so we identify the reward function, which is a linear reward function, and which is decreasing. And it has two terms. The marginal reward has two terms, alpha and beta j, alpha j and beta I. So for actor I, whose neighbor is j and consuming xj, I receives the reward rji of xj. And the marginal reward depends two terms. First term is beta I, which is the marginal externality that actor I feels when at the optimal consumption profile, right? At the optimal consumption profile, xk0, right? And then there is another term which depends on the consumer himself, right? And this term captures the amount of the marginal cost that is incurred by the person who is applying the pressure on the actor. Okay, so we characterize the reward function. Let's now identify what the condition under which the cost of the budget for rewards is smaller than the Pigouvian subsidies, right? So let's consider the first term. The second term is much smaller than the first term and can be neglected in the left-hand side of the equation. So first term is actually just the total marginal externality felt by the whole society, right? And so when this thing is higher than the alpha j, or alpha j summed over all the peers of the consumer, then we see that we can actually achieve our optimal social outcome at a lower price than the Pigouvian subsidies. So these two were the main results. Now quickly summarize the extensions that we have done to this. So important question comes is that when I observe who all are the other people who are exerting pressure on my peer. If there are other people exerting pressure on my peer, I will rather not exert any pressure and reduce my cost of exerting pressure, but still get the reward, because reward does not encompass the pressure I'm putting on it, right? The other problem is that when the utilities are transferable, then people can form coalitions, and I can ask my peer not to put pressure on me, and I will share some of my surplus with the peer on the other hand. The solutions can be found by modifying the mechanism a little bit. First one is to give rewards also based upon the pressure as well as the consumption. But then the problem is that we don't know how to measure peer pressure. And the second one is to extend the rewards not just to the immediate nodes of the immediate neighbors of the consumer, but to the multiple hops away from the consumer. So these two modifications actually solve this problem. Right? Just to finally say what the ongoing work that we are doing in this direction is the study of the effect of peer pressure on the network itself. So what happens when the peer pressure keeps on increasing? There has to be a limit when the relationships break. So we want to identify what the limits are and the dynamics of network under the peer pressure, and what are the properties of stable networks. Finally, we want to also study the heterogeneous relationships, the relationships and the cost of relationships we found. We studied here were homogeneous. We want to see what happens in the difference. And finally, we want to do some experiments. We're planning to do some experiments to reduce energy consumption in DOMs. Thank you.
Thank you, Ankur.
Yes.
So are there any questions in the audience about energy reduction? Yes, I'm coming with the microphone.
Thank you. In your last slide, you talked about the properties of stable networks. So what do you define as a stable network?
So the idea is that when you have peer pressure, it is actually exerting pressure on the social relationships themselves. And so the higher the pressure, there is a tendency for that relationship to break. So there may be situations where the network topology will change based upon what the equilibrium of the game results in. So we want to study the network structures in which, when at equilibrium, there is no tendency for any edges to break. So those are stable networks, which do not break under the pressure in equilibrium.
Okay, thank you again.
Okay. Thank you.